This lesson deals with supplemental problem 214. You can find this problem in the course ebook in the Chapter 2 Supplemental Problem starting at page 15. What's sketched here is a commercial set of headphones, which also has a volume control included with each of the headpieces. The headphones themselves are actually 30 ohms, and roughly 30 ohms versus frequency. I took some measurements between this set of terminals here, which is labeled as L, R, and G, and figured out an equivalent circuit for what's hooked up. Now the L stands for left, the R stands for right, and the G stands for ground. But this quarter-inch plug goes back to the early days of landline telephones, where this was called the tip, the ring, and the sleeve. Now between the left and ground, I found that there was a 500 ohm potentiometer connected to the 30 ohm headphone, and the same thing on the right-hand side. What I was surprised about was that the headphone's resistance was much lower than the pot's resistance. In Supplemental Problem 213, we talked about just the opposite being true, that whatever's hooked up here is much, much greater than what's here, and if you do, you get a linear variation with voltage. I was wondering what the voltage across the headpiece was equal to, so let's see if we can solve for that. Now, what's being applied between the left and ground and between right and ground is effectively a voltage source from the left channel and right channel. So the voltage across the 30 ohm resistance is equal to this resistor, and I'll say that just alpha times the 500, and this will be the 1 minus alpha times the 500 for the left channel. Parallel combination of those two, voltage dividing with the top resistance, which is 1 minus alpha L times 500. Now the expression for parallel is the product over the sum, so I'll take 30 times 500 alpha L over the sum, and the same true over here, and then plus 1 minus alpha L times 500. Now let's multiply through by 30 plus 500 alpha L, and in the numerator that cancels with this term, and in the denominator we're left with 30 times 500, which is 15k times alpha L, same in the denominator, and then 1 minus alpha L times 500 times the 30 plus 500 alpha L. Let's multiply this out. So 500 times 30 is 15,000, and then 500 times 500 is 250,000. Okay, now let's multiply all this out. So I've got 15k times alpha L, 15k times 1, 250k alpha L times 1, and then alpha L times 15k with a minus sign, and then again minus alpha L times alpha L, so I get alpha L squared times 250k. So let's rearrange them by powers of alpha L, minus 250k, plus 250k alpha L plus 15k as the denominator, and then 15k alpha L in the numerator. This is kind of an odd equation. Let me just graph it as a function of alpha L. And you can see you get what looks like an exponential type curve. And I just took some data points here just to show you what the values are. When we're here at 0, all the way to the bottom, we get nothing out. When we're a third of the way, we get 0.0709. When we're in the middle at half, we get about a tenth of the total value. And then as you approach the other end, you're getting more and more of the signal. Now what struck me odd when I was listening to these headphones is that when I rotated the pot, it seemed that it was half as loud in the middle position, a third as loud as in the third position, and so on. But then I thought about what the saying here is that we've got an exponential type curve, but your ear is logarithmic. The two together produce a linear variation with power, which is not the voltage, but the voltage squared, say divided by the resistance of the headpiece. There's a similar plot for the right channel. And what's happening with this voltage divider is that by putting a resistor in parallel with the pot that's much smaller than the pot by about a factor of 10, you get this exponential type curve. And this is Supplemental Problem 214.